In this installment, we'll look at horizontal projectiles and the frame of reference and how that affects what we see. Now, the essential thing to realize is that when a projectile is fired, once that projectile is released, the only force acting on it is the force of gravity, which means that is the only acceleration that it experiences. It's the only acceleration that it experiences, g, downward. It does not experience a horizontal acceleration. So let's imagine we are positioning ourselves way over here in this frame of reference, and we are far away. And what that far away means that as a projectile is coming toward us, the distance that we are away is so far that we can't detect the projectile getting larger as it nears us. Very oftentimes, as something gets closer to us, we can tell it's getting closer because it appears larger. We call that its angular magnification. It gets larger when it comes toward us, or it gets smaller when it moves away. So the reason we are far away is such that we cannot detect the particle getting larger or smaller. So from this vantage point, when we see a cannonball rolling out the end of this cannon and it drops, we see it fall as a vertical dropped object in free fall would occur. But what's interesting is, and not intuitively obvious, is that if we fired that cannon at some high velocity, we will see exactly the same thing. From this vantage point over here to the right, we cannot distinguish between the cannonball dropping directly and the cannonball being fired at some high velocity. The motion will appear the same from this vantage point. So a person over here far to the right would look at this and describe the motion and say, oh, this is just a body undergoing free fall. However, a person located very far overhead, up in a helicopter, say, like so, looking downward at this thing, and again, they are very far, so we cannot detect any change in the apparent angular diameter of the object. What we would see from that vantage point is an object traveling at a constant speed because there is no force acting on it horizontally. Since there is no force acting on it horizontally, it will travel at a constant speed, so we can see the delta x over the delta t. The delta x delta t remains constant, whereas vertically, we see increasing distances. So from our frame of reference, we would describe very different types of motion. If person A were talking to person B on the telephone, A would say, I see an object in free fall. Person B would say, wait a minute, I see an object traveling to the right at constant speed. So they wouldn't even agree as to whether or not it's accelerating based on their viewpoint. And of course, we, way out here in this dimension very far away, we can see the true two-dimensional aspect of the motion. We see more of the truth, two-dimension. From A, we see one dimension, and we see one dimension from point B. It's only in vantage point where we are that we see both motions, both aspects of the motion. And of course, this might be a lesson for all things in life, that our frame of reference gives us a unique viewpoint to see things that other people can't see. We might be looking at the same phenomenon, but actually describe something very different, and both can be true at the same time. So there is an importance to developing thought processes in physics and applying it to our knowledge about the rest of the world.